Welcome back. In this video you will learn how to determine the overall reaction rate of a heterogeneous reaction and how you can improve the overall rate if mass transfer is the rate limiting step in your reaction, or how you can improve the overall rate in the reaction in case the reaction itself is the rate limiting step. We will again look at the example of a first order reaction of reactant A in a well-stirred continuous tank reactor. You have already learned how to derive the equations for the reaction rate. So to do so, we used Fick's law to describe the mass transfer of reactant A over the stagnant layer between the bulk and the interface of the particles, and we also assumed a first order reaction rate for the conversion of reactant A to product P. Finally, we assumed that the reactant concentration at the gaseous and the liquid interfaces were in equilibrium, and that all the reactant that is transferred to the interface should be converted, or in other words, that your mass transfer is equal to your reaction rate. So we now have one equation that tells us the overall reaction rate based on the mass transfer in the gas phase, and another equation that tells us the overall reaction rate based on the reaction at the interface. But both equations contain the concentration of the reactant at the interface of the gas. And to be honest, that's not handy, because in practice we cannot measure this concentration. We can only calculate it. And if you cannot measure it, you cannot determine the overall rate, Ra, not via the mass transfer equation and not from the reaction rate equation. But we do have two equations for the overall rate and one unknown, so we can combine those two equations into one equation and get rid of the unknown concentration at the interface. Of course, it's possible to combine them by substitution of the unknown concentration at the interface from the first equation into the second, but that's quite a tedious job, so I will use the echelon method to combine both equations and to eliminate this unknown concentration at the interface. So I'll start first to multiply both sides of the top equation by 1 over kGa and the bottom equation by minus m divided by k1. If both resulting equations are added up, we get another equation, and you see that the interfacial concentration CAGI cancels out. The overall reaction rate is the overall first order rate constant times the bulk concentration in the gaseous phase. Let us have a closer look at the first order overall rate constants that we obtained. The first term gives us the mass transfer coefficient, kGa. And if the value of this kGa is small, the mass transfer is obviously slow. The second term, m divided by k1, tells us something about the local reaction rate. And if k1 is small, the local reaction rate will be small as well. So if the term m divided by k1 is much smaller than the term 1 over kGa, the overall reaction is limited by the mass transfer. The only way to increase the overall reaction rate is by trying to increase the mass transfer rate. So by increasing, for instance, the value of kGa. And this can be achieved by more mixing or by smaller catalyst particles, so that the interfacial area between gas and particles increases, or maybe by decreasing the size of the gas bubbles that you enter. You may also think of increasing the temperature, as this will increase the Kg value. It's also possible that the term 1 over kGa is small compared to the term m divided by k1, and in that case, the overall reaction is limited by the local reaction rate. If that's the case, the only way to increase the overall reaction rate is by improving the local reaction rate via this K1. And remember that K1 is the rate constant times the catalyst concentration. So if you increase the catalyst concentration on the particle surface, the overall reaction rate will increase. You can also increase the temperature a bit. That can also help to increase the reaction rate, but beware, because it might have possible negative effects, and it increases also the inactivation of your catalyst, and that's something you don't want. So in this video you learned how you can determine the overall reaction rate of a heterogeneous reaction and how you can improve this overall rate. This overall reaction rate can then be entered in a mass balance over the whole reactor to calculate the required volume of your reactor. I'll see you later.